Hello everybody, my name is Dio and today I will show you our newly developed decentralized storage system. Typically, nowadays, when someone wishes to build some sort of application that needs to share state between the different devices, they follow this type of architecture. In this architecture, we have a dedicated infrastructure that is in charge of storing and propagating the different changes made by the different devices and ensuring that every device has access to the same data. And this is usually done by using some sort of distributed storage system or a distributed database. And while this works in a lot of scenarios, as we can see by systems being deployed and used nowadays, may not be the best solution for every scenario. For instance, if you have a scenario where clients may have a bad internet connection or are in high volatile environments, it may be very difficult for them to communicate with some sort of server that may be very far away in some cases. Or if we think in a more specific scenario, where information should only be seen or is only relevant in a specific geographical location, it may not be a good idea to share this information with some sort of centralized server. And thus, this information should only be visible for clients that reside inside this specific geographical location. With this in mind, and to face the challenge that we talked previously, we came up with the following proposal that removes the necessity of having some sort of dedicated infrastructure and where the data is stored directly on the devices, and all of the synchronization and propagation of information is done by every device that is a participant on our system. With this in mind, we came up with Nimbus, which is once again a fully decentralized storage system that doesn't require any sort of dedicated infrastructure, and storage, all of the data is stored inside the devices that use the system. To achieve this, we use CRDTs, so conflict-free replicated data types that ensure that the nodes are able to synchronize the state between each other and offers by design ways of merging state without the need of having any further application logic. It offers a simple key value store interface that I'll explain further ahead. And once again, since it doesn't require any sort of dedicated infrastructure, it supports a very large number of nodes on the system. So in here we have the data model that we propose in Nimbus. And as you can see, the data can be stored in different key spaces that can symbolize any sort of high-level entity. Inside the key spaces, we can have subsets of this high-level entity that can be more specific, that are represented as different collections. And inside these collections, we have the CRDTs that I talked previously with the key value interface. So this means that we can have a key that can symbolize any sort of identifier, and mapped to this key, we have a CRDT that has the data that we wish to store. This CRDT can be of any sort, so a set, a counter, a flag, or other more complex data types such as maps, so that we can have composite and more complex data types in our storage solution. So now we will merge all of this together and talk about how can this be integrated into TARDIS. So once again, Nimbus is a decentralized storage system that can be used by any use case or work package that may benefit from it. For example, if we have some sort of application where we have swarm nodes that need to share some sort of metrics between them, they can use Nimbus to ensure that all of this state will be propagated to the different nodes inside the swarm. Nimbus is as generic as possible, so it can be integrated into different scenarios or different applications without any problem by the developer, and it can be accessed through web services, as I will explain further ahead in our demonstration. And to finish, it may be leveraged to implement federated learning, as for instance, each node stores its data in transit's local model, and then when it wishes, it can propagate the results of the train to the different devices so that they can make an aggregation and train the global model in a way that they can use to infer some sort of data in the future. With this, in order to test and showcase Nimbus functionalities, we developed a website application that enables the evaluation and rating of presentations or demonstration as the following model. First of all, we have, as I said previously, a user interface that is a website written in React, a JavaScript framework. Then we have a REST API that receives the UI operations from clients and sends these operations to Nimbus, as well as a WebSocket that receives operations from Nimbus in a reactive way. So when new updates arrive to each device, and sends these applications to the user interface so that the client can see the updates happening in real time. Then, to make the bridge between Nimbus that lives in Babel, a Java framework, and the user interface, we have a Babel application. This Babel application contains the application logic, and to finish, we have Nimbus that stores and synchronizes the application data, as well as more protocols that live below Nimbus, namely to ensure the synchronization and duration of data, but I'll not get too much into detail in this presentation. So if you are interested, you can always see the code and details of this application in the CodeLab repository of Tardish under Nimbus examples. In here, we can see the data model of our application, where in this case we have only one key space. Inside the key space, we have different collections that represent the different presentations available in our application. Inside each collection, we can see the different objects that represent a presentation. We have first the presenter that symbolizes the presenter name, that is a register. The participant set that we have the participants that are or that attended this presentation, as well as a list of questions, as well as the questions rating that are being continuously updated as new questions come in by the different clients, as well as new updates are issued to previously created questions in the storage system. Now, to test our application, we come up with this architecture and this setup where we have different devices, namely different Raspberry Pis and laptops. Each device has its own version of the data storage, and the devices will communicate with each other to ensure that all of the updates are brought to every device on a system, and to ensure that eventually every node in the system will have the same view of the state. And with this, I will start by showing our website application. To use the website, one must only be connected to the local network where the application is being served and use its favorite device to connect to the website. The website is being offered by the different devices on the network, namely the different laptops and Raspberry Pis. And to enter the website, one must only use the IP address of one of the devices. As you can see that at the moment I'm using the IP address of the Raspberry Pi that ends in 205. By entering the website, we can see that before we enter the application, we need to use a username. So for example, here at Jesus. And when we enter the dashboard, we can see the different applications or the different presentations under the application. If you look into a presentation in more detail, we can see its type, its name, the name of the presenter, and the number of current attendance. And if we enter in one of the presentations, for example, the fundamentals of computer science, we can see the questions that were previously created under this presentation. As you can see, some of the questions may appear to have a bit of gibberish in their name, and that's because some of the Raspberry Pis are being autonomous and thus are making operations in an automatic way to make the system more lively and more realistic. If we look closely, you can see that we have two types of questions in our application. So we have questions that we can rate from or as a thumbs up or a thumbs down, and application and questions that we can rate from 1 to 5, where we can see the average on the top right corner. If you go to the bottom right corner of the page, we can add a question as well, and as long as we give it a description and the question type that once again can be a rateable question or a likable question. And you can see that the question is being added to the system, and eventually every device on the system will receive this information as well. And as you can see, we are at the moment receiving questions being issued by the other Raspberry Pis that are making the system autonomous. So with this in mind, we can, as I said previously, we can access this website through any device. And at the moment, I have an Android device connected to my laptop that, as you can see, is connected to a different device, namely a Raspberry Pi that's under the IP 207. Now, if I search the username, I can access the lectures as well. And then if I go, for example, once again to this lecture and add a new question, for example, and create this question, I can see that eventually, not long after, I will receive the update on my laptop. And for example, if I rate this question, I can see that after a while, I will get the rating as well in my Android device. And with this, I finish my presentation. I hope that you like, and if you have any further questions, you can always visit the CodeLab repository that contains all of the information and all the code details. Thank you.